Welcome back, folks. We're going to be talking about the capacitor. I know you've seen this component before in some of your prereq courses, but let's get all the information in one place and maybe focus on what we need to use when we're performing circuit analysis. Okay, so the capacitor is it's a passive element. It can't add energy. It's a storage element. It's going to store energy in an electric field. And the way we're going to do that is take two parallel plates and get them very close to each other. And if we can push a bunch of holes onto one plate and a bunch of electrons onto the other, the electric field that exists between those charges will hold the charge in place until there's a path for it to recombine. So at its core, it's two parallel plates with an insulator in the middle, and we call that insulator in the middle, we call it a dielectric because it's going to set up the electric field that actually stores the energy. So here's my horrible drawing. Get ready. So there's your capacitor. It's kind of 3D, right? I got a little perspective in there. Not winning any prizes for sure. Anyhow, so if we take these two parallel plates and we stick an insulator in between them, let's take some material. It can be air, but more often than not, it's something else. Teflon's a good one. There's some oil-filled capacitors and things like that. But we stick the dielectric in between. If you look at old tuner capacitors in old stereo equipment, a lot of those had air gaps as the dielectric. And then you'd turn it, and the plates would move apart and come closer together, and that would change the capacitance. And that's how the receiver would tune dielectric. Okay, and we have these two plates. Now, if we want to create that charge differential, we have to create that charge differential. So let's stick a voltage supply out here, maybe just a battery for starters, and we create some change in potential energy between the two plates. That's going to lead to a bunch of positive charge collecting on the top plate as I have it drawn here. Okay. And we'll also have a corresponding amount of negative charge on the bottom plate. Okay, that's all if this voltage supply has some voltage V, or battery. The amount of charge, Q, is then related to the voltage differential by the part value, and the part value is going to be C for capacitance. Okay, so the variable, trying to follow the format that I did when I introduced the values way back in the beginning of the class. Remember that? That was good time. Good times is capital C, and we're going to relate the charge on the plates, the voltage across the plates, and the physical capacitance of the individual capacitor using what I think of as the QVC formula, because it's Q equals VC. It's that simple. Okay, so the charge on the plates is equal to the voltage times the capacitance. We're going to measure capacitance using the unit farads, named after Faraday. Okay, so again, it's named after an old dead guy, so it's going to be a capital F. Okay, no alternate unit on that one that I can think of off the top of my head, but that's where we start. Okay, all of these plates can be described using a different formula. So just like with resistors, we can look at the physical composition of the plate, and we can talk about the capacitance being equal to epsilon. Epsilon is the permeability. No, I got that backwards. Damn. Permittivity. We'll talk about permeability next. Permittivity of the dielectric. So how well does the electric field set up in that insulator? And A is the cross-sectional area. Okay, so let's get some of these down here. Permittivity I'm going to spell this wrong. Permittivity. Not a word I spell a lot. Okay, A is the cross-sectional area. And D is the distance between the plates. Okay, so if I have a better dielectric, it's going to increase the capacitance. If I have a larger area, it's going to increase the capacitance. Or if I get the plates closer together, I got to make that denominator smaller. Get them really, really close together. I'm going to have a larger capacitance. There's other implications to getting it closer together. Now my dielectric is thinner, so maybe I can't put as much voltage across the two plates without causing shoot-through current, something like that. So there's some other implications, but if we can maintain a good dielectric, we can calculate the capacitance this way, just like we did for resistors. Okay. Where do we go from here? We talk about equivalent capacitances. Okay. Equivalent capacitance. Just like we had with resistors and voltage sources and current sources, we can look at capacitors in series, and we can look at capacitors in parallel, and we can combine them. So the same rules apply. If they're in series, they have to share a node exclusively. If they're in parallel, they have to share the same two nodes. But capacitors are the troublemaker. Everything else combines the same, except capacitors. They're backwards. Okay, when they are in series. All right, so let's get two capacitors in series. There's your schematic symbol for a capacitor. It's just two parallel plates. Okay, you might see another one. I'll draw it up here. It looks like that. That's a special capacitor. It's polarized. And you might see a plus symbol up there. So you've got to put a plus up there and a negative down there. So you might see that schematic symbol as well. Let me just note that for your notes, which I know you all love. Polarized capacitor. When it's not polarized, it just looks like two parallel plates like this. All right, these are in series, and following the format that I did with resistors, we have C1 and C2, and we want to know what CAB is. Okay, now I said they're backwards, and they are. And when we had that problem in resistors, we had to talk about the conductance, right? And we related resistance and conductance by taking the inverse. Well, it turns out there's a similar concept for capacitance. Most people don't know this one. You're going to be smarter than most people. How about that? Better educated, hopefully. Elastance, I'm doing everything I can for you. Okay, is the inverse of capacitance. Okay, so when they're in series, the elastances add. Okay, so elastance. The variable for elastance is capital D. I'm not entirely sure why. Part of me suspects that it's just like the letter that comes after C. You know, there's only so many letters in the alphabet. Okay, and then the unit, I always enjoy this one. The unit of elastance is, well, it's the inverse of capacitance, so it is the deraf. Okay, it's just farad spelled backwards. Anyhow, and we talk about the unit, we notate the unit as f to the -1. It's since that's effectively what it is. It's the inverse of the farad. Okay, so if we're going to make these elastances add, then we have to define them, right? So D1 equals 1 over C1, D2 equals 1 over C2, okay? And then ultimately, DAB is going to equal 1 over CAB. And that's the thing that we're really looking for. Oh, it's behind my head. That's the thing that we're really looking for. So we'll have to solve for that. Okay, so D1 DAB equals D1 plus D2. So this is the same situation we had with resistors when they were in parallel, but now for capacitors are the backwards one. It's when they're in series. Okay, so this is going to be 1 over CAB equals 1 over C1 plus 1 over C2. And then we can solve for CAB equals 1 over C1 plus 1 over C2. So, still behind my head. I'm going to disappear. Which way? That way. Okay. So, if there's more, we can add them here. Add more terms here. Okay. So this is similar to what we saw with resistors, right? So if we had more than 2 in parallel, we could add terms down here. With capacitors, if we have more than 2 in series, we just add more terms that are the inverses down here. Now we have the special case of having only 2 capacitors for only 2 caps. A lot of times we abbreviate and call them caps. Only 2 caps in series. We can use that product over sum form. Okay, solving that or rearranging that, we can find that CAB is equal to C1 times C2 over C1 plus C2. Okay, so that's another form, but it has the same limitation. It only works for 2. So don't get caught trying to add factors and terms on the bottom. It's not going to work. Okay. How are we doing? When they're in parallel, what do? This one's much easier. It's still backwards. So we take 2 parallel capacitors, okay, connect them to the same 2 nodes to get 2 capacitors. I'm trying to make these lines as even as possible so you don't confuse them with a battery. Okay, and for this one we have C1 and C2, A and B, and when they're in parallel, it's much simpler. Capacitances add. Okay, so CAB in this case is going to be C1 plus C2. Done. Okay, so sometimes we can use this to our advantage to simplify a circuit. If we see capacitors in series or capacitors in parallel, we can manipulate the values and get an equivalent component. So that's important. It's not the most important. It's not the most important thing we're going to do here. Our fundamental laws of circuit analysis. I've been saying KVL, KCL, Ohm's law. I'm hoping that I've drilled into your head that everything comes back to KVL, KCL, and Ohm's law. And if you think about Ohm's law, it's V equals IR. Okay, well, there's no resistance here. Not in an ideal capacitor, at least. So how do we relate voltage and current? Because that's what we're really after with Ohm's law. When we wrote a KVL, and had to rewrite it in terms of the unknown mesh currents, we used Ohm's law. With a capacitor, at least for now, we don't have Ohm's law. We're gonna play some trickery later. That's pretty cool. We can get Ohm's law back. But for now, we don't have Ohm's law. So we have to understand how we relate the voltage to the current. And that's going to take the place of Ohm's law. Let's see here. We have what I called the excuse me, the QVC formula, and I'm using lowercase because things are going to start to vary. And if you think back to the beginning of the semester, I said when things are lowercase, they're going to vary with time. So we can talk about this as a function of time. Okay, so we're going to start using functional notation more. That's not a multiplication, that's a function. Okay, QVC, let me rearrange it so it looks a little nicer since C is a constant. Okay, and we have the voltage as a function of time. But ultimately this is the same. The charge on the plate is equal to the capacitance times the voltage. Okay, it's just that we're allowing the charge and the voltage to vary. Okay, so we're starting at this, and I'm hoping you got this from physics. That equation's not coming out of the blue for you. If I want to get to the relationship between voltage and current, I don't have current, but we can take the derivative of both sides. And if we take the derivative of both sides, okay, that's my bad lowercase q. I'm working on that. My lowercase t I put a little tail on. My lowercase v I also put a little tail on there because it's hard to discern those. But if you just stick a little tail on it, that one's lowercase. Okay, so I'm going to take the time derivative of both sides. Okay, and c is a constant, so that gets left out of the derivative, and we have c dv dt on the right hand side. Okay, so we're not there yet. Current hasn't shown up. Well, it has if you're paying attention. Okay, current was the time derivative of charge, and that's what we have here. Okay, so we're going to call that I as a function of t, because that was the definition of current, the time derivative of charge, and that's what we gained there. So a lot of times we'll have, here it is in its final form, the capacitor equation. Okay, the functional notation gets dropped a little bit here, and you'll see this written more commonly as just lowercase I, c dv dt. Okay, I equals c dv dt. It's got a nice rhythm to it. Okay, we're going to make that stick in your head a little bit. I equals c dv dt. That's going to be what I use to relate voltage to current in a capacitor. Now you can always write that another way. Okay, that's one of the payoffs there. We can write that in the integral form if we just solve for V. So we can say the voltage across a capacitor is equal to 1 over C. And now we have to take the integral. Okay, we're taking it from t naught at some initial time to our current time, t, and we're going to integrate the current. We've got to be careful with our variables of integration, so I'm just going to say I is a function of t, and we're going to integrate with, or I'm sorry, I is a function of tau, and we're going to integrate with respect to tau, and then don't forget your initial condition. So it's a little messier in this form. I try to write my equations so that I'm using this first form here, but this is equally valid. We do have an initial condition in this one. We got to take an integral, make you flash back to Calc 2, but it's just as useful. Okay, now our equations are going to take on a different form because we're going to start having these derivatives in them. And having derivatives in your equations, if you want to solve them, you have to use differential equations. Now, half of you watching this have had differential equations, and half of you haven't. It's just how this course is set up. What we're going to do instead of using differential equations is learn about something called phasors. We're not there yet, but we are going to take these calculus problems and we're going to turn them into algebra problems, and we know how to solve those. This takes on a little bit of a different form, and we got to learn how to deal with that, and that's where we're headed. Okay, so this is certainly not an extensive treatment of what a capacitor is, but it's the important stuff, and I think it's the important stuff that we need to perform circuit analysis. Next video is the same thing, but we're going to do it with inductors, and then we got to figure out how to do circuit analysis with all this stuff. That's what's coming up. Stay tuned and good luck.